We're going to do an introduction to Chapter 5, Molecules and Compounds. So we're going to talk a little bit about what molecules and compounds are and kind of learn a little bit more about that. So first and foremost, molecules and compounds. What in the heck are we talking about? Well, atoms don't actually often exist on their own. They're not just hanging out singular atoms, not doing anything. They often combine to form molecules and compounds. This is actually what drives chemical reactions, because chemical reactions start with one set of chemicals. They go through some sort of transformation where they break apart and they recombine to make another set of molecules. So as we're making molecules, we have chemical reactions. But we'll talk more about this next week in Chapter 7. And all the time, atoms are breaking apart and reconnecting to make new molecules. So when atoms are hooked together, kind of stuck to each other, we call that a molecule or a compound. We're going to talk about 3 types of compounds in this chapter: ionic compounds, molecular compounds, and acids. Throughout the semester, we'll talk about a few different other kinds of molecules and compounds as well, but that's what we're going to cover here. Okay, so molecule versus compound. Why am I using 2 different words? Well, I'm not really worried about splitting the difference here. So molecule, compound, relatively the same thing. We're talking about kind of one individual unit of some sort of chemical that's not elemental, or singular atom elemental, as we'll see in just a second here. But I'm more concerned that you're able to actually identify something as like an ionic compound, a molecular compound, or an acid. I'm not going to say like, is this a molecule or a compound? Yikes, no, we're not asking that question. I will ask you for the full name: ionic compound, molecule, acid, something like that instead. I'm likely just going to go back and forth with the word molecule and compound, meaning just kind of individual groupings of atoms, like meaning the chemical formula, which we'll talk a bit more about here. So if I mean an ionic compound, I'm going to say specifically ionic compound. If I mean molecular compound, I'm going to say specifically molecular compound. But I might say just an individual word, molecule or compound, to mean just kind of the units that's in the chemical formula, just that individual grouping of atoms, basically. So molecules, compounds, atoms hooked together to form something basically greater than themselves, as we love to say as humans. So elements can actually exist as individual atoms or as molecules as well. So most often, elements are going to exist as these individual singular atoms, okay? Individual little atoms of that kind of element all hanging out together. And anytime we're talking about just the individual element hanging out by itself with only that type of atom, whether it exists as individual atoms or exists as molecules, diatomic molecules in this case, we're going to call that the elemental form. So if I'm only talking about atoms of one type, I'm going to call that the elemental form, okay? So it doesn't just mean always singular atoms, it means any time that you have like one type of atom. So even though you might have individual singular atoms of that element, it may not always be the case that all elements exist this way. So we actually have 7 elements that exist as molecular compounds instead of just individual atoms. So what they exist as are 2 atoms hooked together. So instead of just having one atom of the element, like let's say one individual hydrogen atom, for example, I actually just have 2 hydrogen atoms hooked together. So when these exist at room temperature in everyday life, like, you know, we breathe O2, we don't just breathe individual oxygen atoms. That's what we mean here. So they're just how they exist. So if I mean the elemental form of hydrogen, I mean H2. If I mean the elemental form of chlorine, I mean Cl2, so on and so forth, okay? So if I ask for the elemental form, it has to be given as the diatomic molecule. So I've said diatomic element, diatomic molecule. Well, what does that mean? Well, diatomic molecules are molecules that have 2 atoms in them. Di prefix meaning 2, atoms meaning, or atomic meaning atoms. Who knew? So 2 little atoms hooked together to make those H2, those N2, and O2, and so on and so forth molecules. So really, if you write down H by itself, you mean something entirely different, likely the H plus ion, rather than H2. So you really need to know these elements. You need to identify them as diatomic. It's really going to matter in the next chapter, chapter 7, when we start talking about chemical reactions. So you should always report diatomic chemical formulas if it's a diatomic element. If not, it should exist as an individual atom, and you can just write the individual atom name. So how can you remember this since you got to know it? I always learned it as Brinkelhoff, that kind of weird looking word I've written down there. It's made up of the chemical symbols of the elements. So Br for bromine, I for iodine, N for nitrogen, so on and so forth. So Brinkelhoff is how I remembered it. Choose to use that if you wish. However, However, we do have a visual way to remember them on the periodic table as well. So there are 7 diatomic elements, and they kind of make a little number 7 over here in the right-hand corner of the periodic table. Remember that these are the noble gases, so the noble gases are never going to want to form any kind of molecule, compound, whatever. They are existing as their individual atomic selves, and they love it. However, if we check out this corner right here, we can see that we have 6 elements over here that make the number 7 up, that make the 7 in the corner, the visual 7, right? And then hydrogen, because it's always the odd man out. So these 7 form the diatomic molecules. They kind of make a little L or a 7 in the upper right-hand corner of the periodic table, and then you add hydrogen into the mix too, because it's always the exception for everything, of course. So there's 2 different ways, Brinkelhoff, remembering them how they are on the periodic table. I don't care how you remember them, you just gotta know that these actually exist as diatomic molecules, so 2 little individual atoms hooked together, rather than just singular atoms kind of hanging out. So those are the diatomic elements. And so what I want to make clear too, as we're kind of talking about these monatomic versus diatomic elements, is that we have something called the law of constant composition, okay? So the law of constant composition kind of basically says, like, once you have like a compound, it always exists with that specific chemical formula with those specific number of atoms hooked together in that specific way, okay? So that's why I mean when I say that we have 2 entirely different things when we write H versus H2. The law of constant composition here states that if you have a different chemical formula or you write something different like that, you have an entirely different compound. So even though molecules are always breaking apart, creating new molecules, and if we know that if we have a certain kind of a compound, it always has that same number of atoms and same type of atoms in it, okay? So the ratio of each element within that compound will always be the same. So the law of constant composition, more exactly the way the book states it, says all samples of a compound are always made of the same proportions of the constituent elements that make them up. So basically every single atom or every single particle of a given compound is going to have the same chemical formula. And it's, you know, kind of like, remember we defined elements by their number of protons. Here, we're defining compounds by the type and the number of each atom that make up those compounds, okay? So the reason this works out this way and what happens is that actually when compounds come together to form a compound, they have different properties than those individual elements have on their own, okay? So if you have some sodium atoms and you have some chlorine atoms hanging out, they're going to be doing one thing. If you smash them together and you make sodium chloride, you're going to have something entirely different, okay? So chlorine gas on its own is toxic to us and will kill us. However, we use salt in our everyday cooking life to make our food better, you know? So they have entirely different properties, okay? So different ratios of these different elements that make up these samples of these compounds have different properties as well, okay? So H2O and H2O2, for example. So H2O we know as water. However, H2O2 is actually hydrogen peroxide, okay? So even though they're only made of hydrogen and oxygen, they have two different ratios of hydrogen and oxygen, okay? So we have 2 hydrogen atoms to 1 oxygen atom in water, and then we have 2 hydrogen atoms to 2 oxygen atoms in hydrogen peroxide. And you know, you've used those likely in your everyday life. You know, think about how different they are. Can we drink hydrogen peroxide? No, I don't think so. So, but water is like the necessary for life, and it is a necessity to us. So, think about how exactly differently these behave. So what the law of constant composition is saying is that, you know, if we're going to call something a compound, and it is a compound, it's some grouping of atoms together, that depending upon what kind of elements make it up and the ratios of those elements to each other, we have different compounds that exhibit different traits based upon this. So we can define a compound by its constituent elements and how many of each we have. And this causes them to have different properties. So that's kind of the law of constant composition. In my head, I almost just think of it as the definition of what a compound or molecule is. So lastly, in this video, I just wanted to take some time to talk about different kinds of molecular models we have. So a model is just basically something that is a conceptual representation of something else, okay? So it kind of helps when we can't use the exact literal thing. Like, we're not going to take these individual molecules, hook all the little atoms together, and then like you're going to stick one on your paper, and then that'll be how you turn in your work, right? We're not IBM. We can't be doing that, okay? They were able to take their individual xenon atoms and write out their logo. However, I don't have a scanning electron microscope to read your homework if that's what we're going to do. So a model kind of helps us in a way if we can't exactly do the literal thing, or we might use different types of models to point out different features of things, okay? So for now we're going to look at 3 different types of models that we can use to represent chemical molecules in different ways, okay? So we're going to add more kinds of models to our toolbox as we go along, especially in Unit 3. We're going to add some really important tools. However, for right now, these are going to be kind of the 3 I kind of expect you to be able to look at, interpret, know what I'm talking about if I show you some of these. Or I could kind of expect some other things I'll talk about later too. So chemical formulas. That's our first kind of model, okay? So yeah, it is a model. So we aren't, again, taking the individual atoms and putting them on our paper. We're using the letter C in this example to represent a carbon, and we're using the letter H to represent a hydrogen. So that's a model. It's an abstraction of the actual thing we're looking at, okay? So we're using the chemical symbol, carbon, C, hydrogen, H, so on and so forth. And then we're using subscripts, these numbers that hang below the line here, to denote how many of each we have. We'll talk more in detail about what a chemical formula is and what we can learn at it just a little bit later on in Chapter 5. So this is a chemical formula. This is actually the chemical formula for methane. So methane is CH4. So this is going to give information about the type and amount of each atom you have, the chemical formula does. However, it doesn't usually give you any information about the structure. It doesn't tell you what atoms are hooked together, because realistically, it's not just like a carbon hooked to a hydrogen, hooked to a hydrogen, hooked to a hydrogen, hooked to a hydrogen in a straight line. It makes this more interesting shape that you can see on your screen here. The individual carbon, or the carbon, is hooked to each of the individual hydrogens. It's not carbon, hydrogen, 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 hydrogen in a straight line, okay? So the chemical formula is a great shorthand way to quickly represent specific information. However, we might use a different kind of model if we wanted to give different kinds of information as well. So the other 2 models you see on the screen here are called the ball and stick model and the space filling model, okay? So this first one up here is called the ball and stick model. Each individual atom is represented as a small circular ball connected to all the other atoms, or all the individual atoms are connected together by these sticks, these straight lines, okay? So ball and stick model kind of makes sense, right? This might be what you think of when you take a molecular modeling kit and start to hook atoms atoms together to form these larger molecules, okay? So what these are good for is they give you great information about the structure. It is so easy to see what is hooked to what. And when we start to talk about double and triple bonds, we can represent those in our ball and stick models as well. So it gives us great information about the structure. So if you want information about the structure, the ball and stick model is 90% of the time the way to go. So that's the ball and stick model. However, what do we know about what atoms actually look like? They're a teeny tiny nucleus surrounded by a large electron cloud, okay? They're not these solid individual circle ball things hooked together by sticks, okay? So what the ball and stick model doesn't do is actually give us a realistic picture of what it looks like to hook atoms together and what atoms look like, okay? That's really what the space filling model down here does for us. So in the space filling model, each atom is represented by a large sphere, and where they overlap is a chemical bond. Where they overlap is how they're hooked together or connected, okay? So that's a little bit more realistic for what chemical bonds look like and do. A lot of times, like what we consider to be like chemical bonds, we'll talk about them as covalent bonds later. Those are going to be a sharing of electrons. So look, we kind of see these electron clouds overlap. That kind of represents that sharing of electrons just a little bit better. So when we see these large overlaps of the spheres, it kind of represents realistically what the electron clouds are going to look like, how things are overlapping. So it gives good information about kind of types of atoms and where they're located. And it's realistic. That's good. However, there are downsides to this model as well, so it can be kind of hard to see the atoms and how they're hooked together. In this ball and stick model, it's immediately apparent. However, you kind of got to spend a little bit more time interpreting the space filling model, especially if you have a long carbon chain. So if we look at something like butane versus propane, so propane has 3 carbons with a certain amount of hydrogens, and butane actually has 4. So it can be kind of hard to tell whether you've got 3 atoms in the center or 4 atoms in the center of our carbon chain. So this space filling model isn't as good for seeing what's hooked to what and each individual atom, but it gives you a good idea of what the overall kind of molecule looks like. So what I want you to know about this is that you should be able to look at a ball and stick or a space filling model and determine the chemical formula from it. So there's like a distinct set of standard colors across chemistry that we always see. Some of them can be a little bit different. However, this is what we're going to see representing each of these individual kind of atoms most of the time. So I'm going to use these colors as a standard, and we expect our our book will do the same. These are the colors they're defining they'll use. So I expect you to be able to kind of at least look at the picture, kind of use the key to determine which atoms you have, and then to be able to count the number and type of each atom from there, okay? So we're going to do a little bit of practice of that here. If you have any trouble with this or you think that this is a concern of yours, please send me an email and we'll talk about what to do if you don't feel that you can identify or distinguish the colors in this situation. So just let me know. We'll take care of it. Let's go ahead and practice what this is going to sort of look like. So if we're looking at this molecule that we have pictured on the left, we have 3 different copies of the same molecule. We can tell that it's the same molecule because we have a red atom surrounded by 2 white atoms in this case, okay? So if we see that we have the same colors and same numbers of atoms hooked together in the same way, we have the same molecule, okay? So in this case, we have 1 big red oxygen atom. We can see that oxygen is red here. And we can see that hydrogen is white. So if we have 1 red with 2 whites, we have 1 oxygen with 2 hydrogens. So if we're thinking about that, we have 1 oxygen, 2 hydrogens. Well, what is 2 hydrogen atoms with 1 oxygen atom? Well, that's water. That's H2O, okay? We'll talk about how to write chemical formulas a little bit later in chapter 5, but for right now, we should at least be able to count the type of atoms we have, okay? One last thing I wanted to point out kind of about this in general is that these are going to be standard across like lots of areas of chemistry and textbooks and teachers and so on and so forth. I know for a fact, no matter where you go, you're going to see hydrogen is white, carbon is black, and oxygen is red. My molecular modeling kit I have at home, same thing. Some of this other stuff might vary, but 90% of the time, this is what you should go with. And I mean, this is what the book's going to go with. I'll always provide this to you. But even when you talk to other people or you're looking at other stuff, you'll find this. I actually found the picture of this molecule online for us to practice with, and it had the colors I expected. So even when I'm trying to do stuff like that, we can have, this is why we have standards in chemistry is what I'm trying to say here, okay? So if I wanted to figure out how many different types of each atom I have in this molecule, if I look at this guy here, I see I have one central atom that is a black atom, which we know to be carbon. So I have one carbon atom. I see one little teeny tiny white atom on the top. It kind of looks like a little antenna. So I've got one hydrogen. So I've got one carbon. I've got one hydrogen. And then I've got 3 green atoms down here around the outside. So those are chlorine atoms. So in this molecule, I have one white atom, one black atom. So I've got one hydrogen, one carbon, and then I've got 3 of these green atoms, which are chlorine atoms. So if you have one hydrogen atom, one carbon atom, hooked to 3 chlorine atoms, you have chloroform, actually. So chloroform is actually pretty useful in chemistry. It's a pretty good solvent for organic molecules. So in organic chemistry, we often use it in the lab, and I've used it in the lab myself before, so it's not as scary as you might think when it comes to chemistry. However, I am sure none of us want to encounter chloroform in our daily lives. So you should be able to kind of do some of these activities like this, practice looking at some molecules, determining kind of what kind of atoms are in those molecules. Again, I'll always give you this list, so never fear. You'll have the list of colors. You don't need to memorize the colors. However, you do need to know how to interpret the model that I show you. Okay, so that is it for the first part here of Chapter 5. This is most of the introductory information you will need for the chapter.